Student at Crocs Laboratory at the Faculty of Informatics, Masaryk University. And today I would like to tell you a little bit about our platform, MeeSign, which is open source treasury cryptography demonstrator platform. This is a rough overview. I will start with some motivating example and then get into the details of treasury crypto. So first, let's imagine a simple banking application. So we have some kind of backend service that does the transaction verification. Everything is digital. Then you have some kind of front-end service. There is, let's say, mobile application running towards the end user that does the transaction authorization. From the point of view of cryptography, I'm imagining or assuming that there is some kind of private key that's stored only within this device, and it's sort of representing the digital identity of said user. If the user wants to perform some kind of transactions, he needs to sign these transactions with this private key, send it to the bank, and now the bank does the verification. So maybe the amounts do not match, or there is some kind of problem, or it's actually missing the digital signature or whatever. So the bank rejects, but quite likely everything goes through and the transactions is correct and the respective amounts on the accounts are updated. Now let's imagine that there is some kind of compromise. So we have an adversary. It could be that your phone got infected by malware or your phone got stolen, something like that. But now the adversary has access to the phone and thus also to the private key. And so I think it's easy to see that now the adversary can just issue the same steps to perform the transactions on behalf of the user. So he signs the transaction, sends it to the bank, and now the bank again does the verification. Again, maybe for whatever reason the adversary screwed up and the transactions are not valid, but quite likely he took care of all the details, issued the correct digital signature, and the transactions go through and your bank account is empty now. So that's the problem, and even worse, the adversary maybe is quite handy with technology and can actually exfiltrate the private key out of this device completely, meaning that maybe now your device reports that everything is fine, all antiviruses are working just fine, but unfortunately the adversary still has the private key, and so they can issue these signatures somewhere else without even you noticing this in the future. And so this is something we would like to protect, and the question is like, how can we and whether we even can. I can imagine that you know where this is heading, so we would like to use treasury crypto to fix this problem. So let's go through the example one more time, but now there will be a few more things to cover. There is no simple solution. I'm assuming that now we will have multiple devices. You can say, well, is this reasonable? So the example or what I'm envisioning is like a husband and a wife having their shared account or each their own account, but sort of sharing the balance, or maybe with your close friend, or maybe with your parent, someone you trust. Anyway, so now we have multiple devices. Again, there's a private key, but now the private key is not residing only in this single location, but it's actually split across both of these devices. And it's split in sort of cryptographic sense, so don't just imagine that you split it in half. There is more magic happening behind the scenes. If you want to issue a transaction now, there needs to be some kind of peer-to-peer magic cryptographic dance between these two devices, but it happens only on the client side. And you end up with a valid signature that now you can send to the bank, and again, the bank does the same verification as it did in the single-party case. Again, maybe for some reason there's some problem, so the bank can reject. But the digital signature is backwards compatible, meaning that the backend service, without any updates, can validate that the signature is actually correct, and so the transactions go through, and again the respective amounts on the accounts are updated. How does this protect against the single device compromise? Well, now imagine that the attacker fully compromises one of these devices. And so they have, again, access to the private key, but only to the share or part of the key. And they can try to create some kind of transaction and like somehow create some kind of signature, but this will be always invalid because the attacker does not have a full information about the key. maybe the attacker is a bit more smart and tries to do this dance with the other device, but here comes the multi-party nature of this, where you get the protection because simply, let's say the other party, like your wife, husband, will see some kind of weird transaction sending all of your amounts to the offshore account, and they will just reject and not accept this transaction. So again, the signature won't be created, and so the attacker is no wiser. He can also try to exfiltrate part of the key, but again, it did not help when he had it on the phone and won't help when he has it outside of the phone. It's not providing any more information of the private key. Unfortunately, this is not like perfect case, right? You can see that if the adversary compromises both of these devices, then you are doomed again. And sort of what would be the solution? Well, you might see where this is heading. Well, you will add one more device. And maybe this does not seem reasonable, but you can imagine that this mobile phone would actually be with the bank itself. And it won't be a mobile phone. It would be some kind of backend service that would only hold one, maybe third of the shares for each user. So this has been sort of the example, and now let's have a look more into the threshold cryptography itself. So it was developed in the 80s, 90s, but the concept itself is of course much older, and I think you can sort of recall that like the crown jewels are stored in such a way that you need maybe 5 or 7 people come together, each having their own key, and they open their own lock, and only afterwards they can get to the jewels. In digital world, we have this for, let's say, several tens of years, but it's actually on the rise in the recent years, mainly thanks to a couple of things. In particular, cryptocurrencies' rise caused the need to secure private key better, because compared to the standard bank where if you lose your phone, you will just get your ID, go to the bank, and very likely you will be able to recover your account and your funds. The case for the cryptocurrency is such, at least for the majority. Well, I mean, you can get lost in the details, but in principle, you have the private key, and as soon as you lose the private key, you lose access to your funds. And exactly for that, there are these recovery mechanisms, such as threshold crypto. It's not only cryptocurrencies. In Estonia, they have something called Smart ID, and they are using split key, where they have a RSA key that's split. One part is residing with the user, and the other with like some national or service or somebody, and they are using this two-party RSA. There is also National Institute of Standardization that's running a call, similar to how it has a call for post-quantum cryptographic schemes and primitives. There's an ongoing call for multi-party threshold cryptography, which means there is much more research, much more eyes having a look on threshold cryptographic protocols, which gives them even more sort of popularity across the not just academic sphere. One of the schemes, Frost, is actually being, or I think at this point it's done. It's informational RFC, so not sort of the highest level of RFC you can imagine, but still there is these steps being done, which will help definitely with the interoperability of these solutions. Just to drive the point home, what's the point of threshold crypto? It's the private key operation protection. So we want to mitigate single point of failure, meaning like imagine you have your SSH key on your laptop gets stolen, and suddenly everyone who has access to that laptop has access to the server with that SSH key. The storage of the key, similarly to how I showed you with the mobile phones, is now decentralized. So there is no single location where the key actually exists. Even better, this is possible to be, or this is achievable during the creation of the key itself. So there is some kind of distributed protocol, and the key never exists in a single location. It's just that the parties themselves sort of end up with these shares that allow them to then issue the signature or threshold decryption. Even better, you can think of some kind of policies now, because the ability to do the digital signature now resides with multiple parties, and these parties can have different conditions under which they use their share for signing or for decryption. So I guess, again, coming back to the wife and husband example, both of these quite likely have different views on what valid transaction means and what kind of amount is spendable. And these exactly are the different signing conditions. But now these conditions are sort of baked into the signature. It's in this sense a bit better than just some if statements in the source code, maybe checking this. Of course, I cannot explain all of the technical details in this amount of time, and I don't even know all of these, but I will at least try to give you some sense on how this can be achieved. And one of this is Shamir secret sharing. Here, this is not the distributed key generation, but there is actually one value that we want to secret share across or among other parties. And we want to share it into n parts, such that if we get at least t together, so let's see like 2 out of 3, these two will be able to reconstruct the secret value. However, if you are on your own, you have less than t parts of this sharing, you get no information. There's really no connection that you can make to the secret value, and we would call these t out of n, and the t stands for the threshold. So how would you do it? That's somewhat simple geometry. If you imagine you have a plane with 2 axes, we can plot our secret on the y-axis, and so this is like value 3, whatever, but it would be, of course, much bigger so that it's unguessable. And then you just find 2 points, such that if you draw a line through these points, you intersect the y-axis in your secret. And these are exactly the 2 shares that I've been hinting at. So if you have both of these points, you can draw the line. I mean, you will do some kind of algebra behind the scenes, and you will get to this point. And this is the reconstruction of the secret. However, if you get only one of these points, well, there are infinite many lines that you can draw through this point, and simply there is no way for you to find which one. And I mean, you can try, but it will take you a long time, and you likely won't get there. This solution also scales, because we can have polynomials of higher order than just a line, and so we can have more shares needed. And also we can just add more points to the line, and then you get these like 2 out of more, because any 2 points that you have on this line will form the line, will intersect the y-axis in the secret value, and so you get like 2 out of 3, 2 out of 5, depending on how many points that of course are distinct that you share across your participants. The threshold nature makes it so that now the digital signature is not just simple operation, but it's actually a protocol, right? So the distributed key generation that I was talking about previously, it is a protocol that's running among these participants. However, then in the future, when you want to use these shares or this key for the cryptographic operation, you are only using these shares. This is the core feature. And even better, the way it's, I mean, it's natural that this is where the research is trying to head, or is heading, is the fact that the output is indistinguishable from the single party one. So if I give you single party created ECDSA signature or RSA signature, and I give you threshold one, you cannot tell which one was created via like a threshold group, which one was created by a single party, which gives you the nice property that you cannot like censor this usage of these signatures. The standard signature schemes or cryptographic schemes such as RSA, ECDSA, DDSA, or for decryption like Elgamal are now thresholdized, so you have protocols. The scene is a bit complex, meaning that there is no like one protocol to do ECDSA threshold signature. There are actually many protocols, and so you have to pick one. I also don't want to sell that threshold signatures are just solution to everything. There are, of course, considerations. I've talked about some of the ups, in particular that the key never exists in single location, and that the verification, not the creation, but the verification of the output, such as verifying digital signature, is backwards compatible. You don't have to update your backend quite likely in any way. But there are also downsides, like now we are juggling both cryptography and distributed systems, so this is, of course, more complex. There are some communication rounds, there are interactive, non-interactive variants. The payload sizes can be quite high for just sort of basic signatures. The computation is much more complex on the client, so if you want to run it on very limited devices, this is a bit trickier. And there are practical problems, like you want to discover your peers, you want to share the correct messages to the correct peers, and suddenly you get into all of these problems that you did not have when you just had a single party signature, for example, for your SSH connections. However, hopefully, I've still persuaded you that this does make sense. And if you're asking yourself, like, can I try this now? Well, this is exactly where the MeeSign platform comes into play. And so what is it? It is a fully open source threshold cryptography demonstrator. I'm making this disclaimer explicitly. We are not building like production ready software that we are saying you should go use. This is really just to get a hands-on how this could maybe be of benefit either to you personally or in your organization to make the adoption better for the upcoming years. Of course, it would be nice to have clients for different devices. So we've built a Flutter application that you can run on your phone, on laptops, so you can actually benefit from the multi-party setting. We do have a server that sort of manages the communication, and it's like semi-trusted. There is some first use client registration, and then the sort of further communication is like a mutual TLS, but again, for your production solutions, you would likely pick a bit better as a security here. It has been developed over a couple of years by a bunch of students and researchers, in particular by Antonín Dufka and led by Peter Schwenda. And it's been supported by several projects. So one of this is Ministry of Interior of the Czech Republic that supported the majority of the development, and it's also partially now supported by the Horizon project from European Union. For both of these, we are quite grateful. If you would like to use this, you can use it just sort of on your own with our server, with the clients, but nicely enough, it's also possible to integrate into existing applications. So if some of these ring a bell to you, like smart cards, video tokens, cryptographic hardware wallets, these do have like standardized interfaces, for example, PKCS11. And if your application supports this interface, you can hook our server as sort of a virtual token, and when your application asks for digital signature and provides maybe the message or hash of the message, you can send it through the interface to MeeSign server, which will resend it across the clients. The clients either will accept or reject, and you will get the signature back to your application. So, for example, you can already, and I've done this, I mean, several like months ago already or a year ago for SSH, where we have this PKCS11 bridge application, and like instead of typing your password for SSH, maybe you just click yes on your phone and on your laptop, and you're logged in. Since OpenSSL 3.0, there should be like providers for the cryptographic operations. In particular, there's the PKCS11 provider, which is again like a middle layer between application and the cryptography library. And so and this is something we are now in the middle of testing, but in principle it should work now, is that your application talks to OpenSSL, and you will set it up such that the OpenSSL is expecting PKCS11 provider. And this provider will talk to our MeeSign server, and again, the threshold signature will happen behind the scenes. So hopefully, this will make it quite simple for you to test. Exactly this integration via PKCS11 is something we done as part of another publication for X-Road, which is on the national level in Estonia and in other countries, like a data exchange system. You can imagine as like a digitally signed tunnel going between different institutions and companies. And this tunnel is signed, and these signatures are being done by, or you can hook a token via PKCS11. So we hooked MeeSign, and everything worked out. Again, without any change to the verification software, so I didn't have to touch the Java monolith at all. Only did some configuration. What are the MeeSign features? Well, you sort of need to create a group that will do the signing. So pick the name, participants, the threshold, purpose, whether you are signing PDF or something else. These are more like for the demonstration, of course, for your applications. You would maybe need only one of these. You can also pick the underlying protocol, and then the users either approve or decline joining the group. The supported protocols vary. We have one for ECDSA, for Schnorr. We have some threshold decryption with LGAML. And there are also advanced features where you can like weigh the shares and increase the voting rights on one party because they have more than a single share. You can also store the shares on something like a smart card, and so when you want to sign with one of your shares, you just tap the smart card to the phone and the share is actually protected even better. To see it in action, just like a couple of screenshots. So you have this view of the client, you have your name. When you want to create a group, this is maybe the most interesting. Like you pick a name, you search for the participants, you can set the number of shares, you can set the threshold and then the usage. And now the multi-party comes into play where the users can join or decline. If they all join, you get a group, you see sort of the metadata about the group, and you can use it. If you want to sign with this group, you pick with file picker, you pick your PDF, you select the group that you want to use for the signatures, and this is now the crucial part where the participants can decline or approve signing this document. They can like view the document, of course, and check for themselves. And if enough of them, the threshold of them approves, you get the PDF signed, and you can like check the signature in Adobe Reader or some other reader. And that's basically it. You can view the result here in the application as well. And to conclude, hopefully I've persuaded you that threshold cryptography is practical nowadays, and you can use it. Its main purpose is to defend the private key operation against like a single device or few device compromise. And we have this MeeSign platform, which is fully open source, ready to use, and we are happy to get some collaborators or contributors. Likely there will be issues that you will find, so feel free to hit us on GitHub. There are a couple of links, references, if you have the slides later. And with that, I thank you a lot for your attention. And if you have any questions, I'm happy to answer them. Thanks.